Thank you. Sorry I couldn't be there in person. I got called into a dean's meeting here that I couldn't avoid. And wow, I'm glad you can see my my slides there, but I'm really big on that screen. Okay, so I'll try to look my best to give this talk. So hopefully everybody's enjoying their fall, and I wanted to just give some talk here on. These are just kind of musings a little bit about what we can start to think about doing with sort of these emerging machine learning methods around model discovery from data. And there are a lot of options for us to start thinking about when we use neural network architectures. So I'll just kind of go through this. I'm going to first give you an example to sort of lay down some intuition, and then I'll go into some very specifics of how this might actually work in practice. So this is the basic storyline right there, which there's two aspects of I want to talk about with this, which is one is a coordinate system to be working on, and second is then to express the dynamics in that coordinate system. So it's sort of a two-component mix of making a good model, is both having that right, what we might call a latent space, manifold, coordinate system. These are all sort of really representing the same thing. And if you get a good one, or if you can build a good one, then you have this potential of writing down a very nice model or expressing your dynamics in a very nice way. So that's really what I want to start focusing in on. And it turns out there's a lot of options for you here about pairing these coordinates and dynamics together. Okay. So this was in the background of my first slide, and that was, of course, intentional, which is what you're looking at is the retrograde motion of Mars in the night sky. There it is, traversing the night sky, and here's Saturn. And this was, of course, the most important of the ancient this was physics for millennia, is to understand the motion of the planets, right? Celestial mechanics has a deep history. And people from the ancient onward were trying to understand and predict the orbits of the planets. So this is the observational data. And then what can we do with that? Well, people started very early on thinking about how to write down models for this. And in fact, the earliest successful model of this was the Doctrine of the Perfect Circle, which came out of 2nd century Alexandria, Egypt. And interesting, this was the sort of, in some sense, the intellectual hub of the ancient world. Alexander the Great, as he swept through from Macedonia down to Persia and Egypt, he actually, the Egyptians were not open source people. They hid their knowledge, but once he conquered them, he took all these manuscripts and so forth and started collecting them together. And one of the people who had access to this was Aristotle, who was the teacher of Alexander. And so you start this rich intellectual tradition there in Alexandria, Egypt, and in the 2nd century emerges this idea of the Doctrine of the Perfect Circle. And these are some ancient, some Renaissance paintings about this, which was the idea is that you could describe the motion of planets as circles upon circles. And so this is another way to think about it, is the earliest version of a Fourier transform, right? So you represent the cycles, these retrograde motion as simply a sum of cosines, if you want to think about them. And so this is an early theory. It lasts about 1,500 years. And of course, this theory came down. And so we are taught in school, of course, and this is sort of more a different coordinate system, is that in fact we have a heliocentric coordinate system. And this was really advocated. Copernicus kept pushing this idea, and it was really the foundational mathematical work of Galileo and Kepler that pushed us into this coordinate transformation, which was the reason you see the retrograde motion is because you are observing that planet from yourself being in a moving coordinate. And so if you start to now frame the coordinate system as heliocentric, then you start to understand that your planetary motions are these ellipses, essentially, going around the sun. It was within that context that once you have that coordinate system established, that Newton, about 80 years later, after Kepler had famously wrote down his sort of Kepler laws, came up with F equals ma as a description with the inverse square law, distance law, of F equals ma type model for the physics of the celestial mechanics. So that wasn't possible until you had the right coordinate system. So this here represents this idea of a coordinate system with models. Of course, as we improved observations, so often has happened in history, when the late 1800s, early 1900s, improved astronomical observations, basically showed us that there was something not quite right with F equals ma, and in fact, this led directly to the Einstein positing general relativity. So that was only possible through these better observations of the planetary motion, where we could see a discrepancy between the F equals ma physics and the actual orbits themselves. Okay, so that's so let me just highlight this, because this hopefully makes a lot of intuitive sense, but it's going to be framing everything we do here, which is, so there's two models that are possible here, right? Model one is this here. Let's bring it back into the context of that picture I showed you, which was coordinates followed by dynamics. And so what we want to do, if we took pictures of the night sky here, so if you look at the retrograde motion, so your data is this pixel space. In the first model, the Ptolemaic model, what you would find is that what this neural network coordinate discovery mechanism is aiming to do is to discover a model where this is the dynamics in that model. In other words, the Ptolemaic system, which is give me a set of circles, as well as the frequencies around the period of oscillations around the circles, and that is a description, perfectly valid description of, in fact, the planetary motion. And so, and then this is like it's also set up as an encoder, which is my original measurement space here is very high dimensional, and I've pushed it down into a very low dimensional representation, which is essentially the number of frequencies that I want to be using to describe that motion. And then I can come back out with the decoder, which takes me back up to the original system. So that's one model. A second model, instead, is the one we typically think about, which is heliocentric system, which is I want to take, again, this high dimensional measurement space, which is pixel space observations, and I want this encoder to learn this coordinate system. And this coordinate system here is our heliocentric, where now the Earth, the sun is at the center of this coordinate system. And then in that coordinate system, you would learn your F equals ma physics. I'm picking up some sounds here. If someone was moving. Can you guys hear that? All right.
Yeah, sorry, I muted her.
Oh, okay, great. Sorry about that. All right. I wasn't sure if there's somebody there. All right. So anyway, these are these two paradigms for what we're thinking about a little bit. And so so again, we're going to start from data. So here's the mathematical framework, right? I have some dynamical system. And what we're going to kind of assume here is, at least initially, is that I don't know the dynamics. So what I actually have are just measurements of the system. So here is my measurement y of t of k. In other words, I measure at different time points, discrete time points. I don't necessarily even know what the right state space variable is, nor the dynamics, nor even the map for my measurements to the state space. So for instance, if you are doing looking at these whole brain recordings in neuroscience, it's not clear we know what the right variables we should be using are, right? And so there is this question about if I can take data and from data learn all these things that are important, like what should be the right coordinate system. Okay, that's in some sense what X is. What should be the dynamics in that system? That's what F is. And so the question is, can we use these modern machine learning tools, in fact, to do that? And I will show you that, in fact, that is something you can start to do now with these techniques. And it's really, this, by the way, is a terribly ill-posed problem, right? Because you're going to try to get from measurements, you're going to try to discover H and F and X and the parametrizations. So this is terribly ill-posed. So in grad school, I like to tell everybody, like in grad school, if someone says a problem was ill-posed, then you would, go find another problem to do, because you never get your PhD if you're because it doesn't have a solution. And now, when I think about ill-posed problems, that just means you need to provide extra regularizers or extra constraints to make it well-posed. And that's exactly what we're going to do here, is we're going to set up a neural network architecture to solve this, to make this ill-posed problem well-posed. And I want to direct how it does that by setting up the right kind of constraints and priors into the system. And that's very nice to do with neural networks, because that comes into the loss function that you would be applying to this model discovery piece. Now, again, I just want to emphasize, you have a lot of options about what you might want to learn. And I want to give you one slide highlighting this, because typically, and this is why I gave the title I did, some thoughts on governing equations, because normally I had been thinking about this a lot in the last number of years as, what I really would love to do is discover the governing equations of a system. So for instance, think about this here as a governing equation. Berger's equation is my first nonlinear PDE I learned in grad school. And, I learned that it creates shocks. And then, of course, you can regularize the shocks with a little diffusion. And so, it was a fun little problem to learn quite a bit about. And here's what's interesting about Berger. So I may have some data and maybe I would learn Berger's, and that's a representation of the dynamics. But Cole and Hoff in 1950 independently discovered this transformation here, which we call the Cole-Hoff transform, which if you change u to a new variable v through this transformation, then v satisfies a linear heat equation. Now, this is quite nice. A linear equation, I know how to solve that. I know how to actually, this is pretty simple to do, right? You Fourier if it's on an infinite domain, you Fourier transform it, and or if it's on a bounded domain, you can just do a spectral decomposition. So this is a really very easy problem to solve now that it's linear. Not only that, it's only got 2 terms instead of the 3 terms that it had before. So it's more parsimonious. But even if I gave you the heat equation, what would you do? Well, what we were taught to do is you solve it, right? So another way to think about it is, here's one solution type with on a domain 0 to L with 0 pinned boundaries, is you might get some solution to the heat equation that looks like this, right? It's some signs, these are your modes in there. Here's your time dynamics, which are exponentials that are decaying. And this would be some sum from 1 to infinity. Of course, you wouldn't do 1 to infinity. You could go to some n. So why not just learn this directly? So in other words, part of what I'm advocating here is, when you set up your neural network architecture, you could say, what I want to do when I come back to this problem here is I could learn the governing equations, the right state space variables. What I'm already showing you there is, what do you mean, what do you want to learn? Do I want to learn this Berger's equation? Isn't it simpler to learn maybe a linear equation? Isn't it simpler still to learn just the solution directly? There are reasons you might want to learn each one, but these are all options for you. When you train a neural network, you can say, which one of these am I going after? So it's not just the governing equations. You could learn 2 different versions of the governing equations. The only difference between them is the coordinate system, okay? Or you could learn some representation directly of the spatial temporal data that you have, right? So you could encode this and, use some convolutional autoencoders to build some kind of construction of all of this data and compactify it into some neural network architecture where you could expand this, right? And then, of course, there you might lose interpretability, but it's still a perfectly valid way to learn a model for the Berger's equation. So my hope is that what this shows you is, immediately when you start to think about model discovery or taking data and building models from data, which is kind of where I spend a lot of my time, you start to have to make choices right away in that design process. What do you want out of the system? What do you want to learn? Because you're going to tell your neural network to go learn it for you. Okay, and here's the thing that we are going to really spend a lot of time with regularization. The one thing that I am actually very interested in is this idea of being able to build interpretable models, interpretable and parsimonious models. So these concepts go way back to, William of Ockham was really kind of at the the beginning of this. And part of why William of Ockham was at the beginning of this is because during the 1200s, he was at Oxford, and they had just been rediscovering Aristotelian logic. And they were making these very amazing constructs of logic. And William of Ockham said, no, we should make the most nominal models possible for logical constructs. All this other stuff that they were building were superfluous and were completely unnecessary in logical constructs. And so he was really advocating these nominal models in the context of Aristotelian logic, okay? And this idea has pervaded the sciences for a long time. I put Pareto here because we often talk about Pareto optimal solutions or Pareto frontier, which is, again, how do you find a model that does a really nice job explaining what the observations, but it's sort of has the minimum number of terms and dimensions, as it were. So that's really what we're going to go after, are these concepts here, which is when I look at that ill-posed problem, I don't just want a solution. I want a solution that, in some sense, is in the nascent dynamics of the actual system itself. So in other words, I want the smallest number of dimensions I could use and the smallest number of terms so that I have some potential to accurately describe what I'm seeing. Okay, so let's start off with some options here. So option one, just like I showed you in the burgers, right? There is a Kohlhoff transform that you can just learn how to move the burgers, not your PDE, to a linear model. And so that's like a version of what we call Koopman theory. So I think you might have heard quite a bit about that yesterday from Igor Mezic. And Mezic and Rowley, Schmidt, others have been really done a lot of pioneering work here in terms of setting up the infrastructure of Koopman. And so let's talk about what that would look like in terms of a neural network architecture. So we're going to start here, and this is work. I mean, and mostly what I'm going to do is feature work of my students and postdocs because they did of course everything, and so I just get to be the spokesperson for them. But this is work with Bethany Lush, who's now at Argonne, and what Bethany did is we said, okay, let's try to, the Kohlhoff is very special. Like if you can find these analytic transformations, it's fantastic. But after Kohlhoff in 1950, there was about a 20+ year gap to the inverse scattering transform, which was another analytic transformation for a class of complete integral PDEs like nonlinear Schrodinger, KDV, and we haven't seen any linearizing transformations since. So it's been 50 years. So they're very difficult to find in terms of an analytic expressions. So what we wanted to do instead is use our neural network architecture, let the neural network learn the coordinate transformation. In other words, why don't we just have this neural network learn the Kohlhoff transform, as it were? So we're going to start off with an initial space that we started with, where we collected the dynamics. And here we're going to actually start off with doing just the pendulum problem. It's sort of one of the simplest dynamic systems problems you can think of, but it turns out it's actually quite tricky as well to encode. So I'm going to start with that. Here's a nonlinear pendulum. So this is theta double dot is negative sine theta. And I'm going to try to move it to a coordinate system y. This is my latent space, or my new coordinate, where in this coordinate system, when I go from y of k to y of k plus 1, in other words, I take one step into the future, there is a linear map. And if I take multiple steps, then it just, it's repeated multiplication by that matrix. Notice also that we've compressed this down to 2 dimensions, because I know it's a pendulum system. So I know that underlying rank is 2. Now, it's very easy to build a linear model if you go towards infinity. So in other words, if I were to take this and say, I don't really care if this is at rank, as a 2-dimensional system, I just go to infinity here, then it's really actually quite easy. If you project to infinity, then in fact, actually, you can build a linear model very nicely. What you lose, though, is interpretability of those models. So what we really wanted to do is move into a coordinate system, but that coordinate system is at the right dimension of the underlying physics you're trying to model. So we tried this with a simple pendulum, and it turns out it's actually it was quite difficult because if you have a 2x2 matrix in here, of course, you only have a couple eigenvalues. And as the pendulum swings higher and higher, then you get this frequency shift that happens. And so what we did is this is really just a manifestation of the continuous spectrum of the pendulum. And so what we did is we trained a subnetwork to parameterize that 2x2 Koopman operator as a function of that frequency of the swing. So this allows you still to build a 2x2 model, a linear model, but it has this parametric dependency which captures the continuous spectrum. And so you can do this. You can take this pendulum, and here's the pendulum data, and here are these, it's really easy. When it's a small oscillation, it's essentially linear. And so that's not something you need to move into a new coordinate system. But now if you look here, you'll see that, in fact, these oscillations start to become, they're no longer just nice sines and cosines. In fact, they're more like Jacobi elliptic functions. And then the question is, how can I make those linear? Well, this coordinate transformation will take this phase plane here, which is, this is our standard phase plane that we have, and it will turn it into circles. So essentially, you can actually learn this mapping over for the pendulum to make it completely linear in this new coordinate system using this encoder-decoder structure. A harder problem is flow around the cylinder. Here's flow around the cylinder. So now you can just take this nonlinear dynamics here, again, do the same thing, learn a transformation for the low rank aspects of this full PDE, and you find a 3x3 model, and it's, in fact, you can make it linear in that case as well. So again, you took this nonlinear dynamics, produce a linear model out of it. Finally, this one, I think, this is with Craig Jin. Craig joined us, and Craig and Bethany, along with Steve Brunt and I, started working on a little bit harder PDEs, which was the Kuramoto-Shibashitsky. And Kuramoto-Shibashitsky is a very complicated spatial temporal dynamics, right? So you get the spatial temporal chaos and so forth. And so we thought that we had no shot at this, but we actually tried to see, can we find a coordinate system in which the dynamics of the Kuramoto-Shibashitsky become linear? And in fact, we were able to do that. So in some sense, this is like the inverse scattering transform for the nonlinear Schrodinger, but you're finding it here for Kuramoto-Shibashitsky, which exhibits spatial temporal chaos. So here's, for instance, the exact solutions simulations. Here's our linear model going through this encoder-decoder network. And it really does an amazing job that you can approximate the full nonlinear dynamics by this linear model for these different initial conditions, different behaviors. And so it tells you something that maybe we're still missing some tools to linearize nonlinear PDEs, because clearly we can do it with a neural network. And so maybe that gives us something to go after with analytic tools, because it's been 50 years since we've had some prescriptive way to do it. And of course, this is a computational technique, but wouldn't it be great if we could find some theoretical basis for these transforms as well? All right, so you can also, instead of warping space, essentially what we were looking at is trying to find the right coordinate system by making transformation of the space. We can also warp time. So instead of working with, so essentially what Koopman's going to do, since the linear model, is going to try to do exponential fitting. And really, we're mostly interested in persistent dynamics, which means the exponentials are going to be complex parts, which is oscillation. So let's take data and try to do a fit directly to what a Koopman model would be, which is sines and cosines. So one way to do that, it's sort of like a Fourier transform, except this Koopman fitting doesn't require periodic boundary conditions on your domain. Okay, that's a big difference. And this is work with Henning-Lange. And what we did is we did more than just fit tech cosines and sines, as few as you can on non-periodic domains. We said, okay, but wait a minute. Suppose you have a time series like this one, where you have sharp structures. It's still periodic. It's just the problem is that if you do Fourier modes, these sharp structures are going to cost you a lot of Fourier modes to represent this correctly. What if instead we learned a neural network, this is the f of theta, where you take your time series and you warp it to make it look as sinusoidal as possible, and then you fit your sines and cosines directly to that. And in fact, that's what we did. And it has amazing performance, even if you're looking just from a time series perspective, comparing it to standard leading techniques in neural networks like LSTM, gated recurrent units, echo state networks, as well as statistical methods like autoregressive models. So we compared it against, the standard statistical time series methods, as well as the leading neural network, recurrent neural network architectures. And using this Koopman forecast trick, you do better in every regard in terms of medium, long, and short forecasts. It's quite remarkable. And we did this on power grid data, which has quite irregular behavior, but it's sort of, long. It still looks, there's a lot of periodic structure to it, but it's all quasi-periodic. And you can also use this for building, for instance, reduced order models. So this is, for instance, if you take this PDE and you look at the low rank subspace on which the evolution occurs, you can then take this model that we built here and then build a time projection with this Koopman method. And so now what you see here is we have a very fast reduced order model that is actually stable by construction. So this is much better than, let's say, a Galerkin projective model, because first of all, it's stable. Second of all, it's really fast once you get the Fourier modes out. And now you can predict way out into the future with this thing, and it's quite accurate when you do this. So those are linear models. So, right, I made a choice. I said, I can have some choices. So why don't I try to find a coordinate system to pair with a linear model? I could now instead say, find a coordinate system, pair with a nonlinear model. And this is this architecture was called the SINDI, which is sparse identification of nonlinear dynamics. And so the idea here is pretty simple, actually. This is just AX equal to B. So whatever you see on this slide, just think AX equal to B. So let's talk about what A and X and B are. So what I'm going to do is collect data from a dynamic system that I'm measuring, okay? And I don't know what it is. I just have, let's say here, it's the Lorentz system, but I give you time series data for X, Y, and Z. And I don't tell you what produced that. Well, if you have that time series data, you can actually differentiate it. So you can produce X dot, Y dot, Z dot. So that is B in the AX equal to B. So that's here. So this is here, the AX equal to B. B is the differentiation of the time series data. And now we're going to say is, well, I don't know the dynamic system, but I know it's X dot equals F of X. All I need to do is discover what is the F of X. Okay, what A is a library of potential candidate functions that make up F of X. So you can pick up your textbooks, and we've studied dynamical systems for a lot of time. And so we have lots of great models. So you can make a library of all these potential terms you've seen in dynamical systems. So these are each column element is a different library term. That's the matrix A. And you can evaluate these at each time point because you have X, Y, Z. So you can put in and evaluate each column in time. What B is the coefficient of these library terms. So these are the loading functions of how much does each one of these library terms contribute to modeling X dot. So in other words, if I have X dot equals F of X, I'm trying to figure out that F of X, what is it made of? And what we want to do here is do a sparse regression. We don't want to do a least square regression. The least square regression would say all the library terms that matter. Sparse regression says how few library terms can I use and match that derivative data. So that's what SINDI does. So it's AX equal to B with a sparse sparsity prior on it. And so when you do that, you actually find, you do the sparsification, you find, oh, here are the non-zero terms. What are they? They're exactly the Lorentz. So you recover the governing equations just by doing that sparse recovery there. You can do PDEs.
Sorry,
yes.
Just another to have 5 minutes. Yeah, thank you.
Yep. So here's the PDEs you can discover with this. So you just take spatial temporal data and said, what generated the spatial temporal data? You use this architecture. You can do it with PDEs, and there you go. You can get all, here's all the canonical PDEs I learned when I was in grad school. So there they are. Okay, so up to this point, notice that with this SINDI model, I had the right variables that I measured. In general, you may not have that. In general, you may,